Okay, so today we will discuss about Ohm's law. Okay, Ohm's law, resistivity, temperature dependent of resistivity. I mean, how resistivity depends on the temperature, and we try to solve some numerical on that. What is how inverse of resistivity is conductivity. That also we will discuss. Okay, so in your book there is a good example. Not going into details of that theory, I'll just start like the so if you have, let us say you have a conductor like you have a conductor. Okay, so let us say you have a you have a conductor and so let us say you have a conductor like this. Okay, so a conductor of rectangular cross-section. Okay, so you have a conductor. Okay, so let us say this conductor has area of cross-section A. Okay, let us say the length of this conductor is L. Okay, so if we let us say if we cut this conductor two different cross-sectional area. Okay, so we cut it here and put two conductor one above the other. The same length, but we put two conductor same length like A by 2, A by 2. So let us say A, let us say this is A by 2 and this is A by 2. Okay. So what will happen? Like current is nothing but flow of electrons. So if you have half the area of cross section of the conductor, half the current will flow through this and half the current will flow through this.
Yes.
Okay. So your current has decreased. Okay. So like as per Ohm's law, V is equal to I into R. Okay. So V is equal to I into R. So R, we want to develop a relationship with R. So R is equal to V by I. Okay. R is equal to V by I. So now that you have reduced the cross section to A by 2, what has happened? This in place of A, so when the area of cross section is reduced to A by 2, when area of cross section is reduced to A by 2, the current flowing through it is I by 2.
Yes.
Okay. So through this I is flowing, through this I by 2 is flowing. So what will happen? Like in place of V, in place of I, but this new condition. Let us say this is condition A. Let us say this is condition B. So for condition B, what is happening? R is equal to V by I, which is nothing but I by I means IB you can say. IB you can say. Okay. In condition B, is nothing but I by 2. Okay. So so 2V by I. Okay. That means this is RB. Okay. In condition B. So in condition, so it will become initially in first condition the resistance was R. So it has become 2R. Okay. That means when the area of cross section decreases, resistance increases. Okay. So when area of cross section decreases, resistance increases. That is proven.
Yes.
Okay. That means you can write R is inversely proportional to cross sectional area. Sorry, yeah, if it decreases, resistance increases.
Yes.
Right? So when area of cross section decreases, resistance increases. That means a thin conductor will have more resistance. A thick conductor will have less resistance. Because it will have more area of cross section for flow of electrons.
More area means
It's
less
just a
resistance.
flow. It's a flow. So something is flowing. If you are reducing the cross section, the resistance will increase. That's very obvious. Okay. Similarly, if we put two conductors one behind the other here, if we put two conductors one behind the other, the length will increase. Okay. So you can prove also, you can see that we can prove that if length increases, resistance increases. Okay.
Yeah.
So if length increases, resistance
Then it
increases.
becomes 2L.
So yeah, it becomes 2L and the current will become 2I. In this case, your current has become I by 2. There it will become like not exactly 2I. The resistance will become, the R will become 2R. Because here the voltage will be V, here the voltage will be V, and R will become 2V by I. Current will remain the same. Current passing will remain the same.
Potential
will increase 2V by I. Okay. So it becomes 2Y. So in this condition, for this, let us say A, B, let us say this is C, where two conductor of length L are placed one after the another.
Length is increased.
So this is condition C. Length is increased. Cross-sectional area remains same. So it becomes 2B by I, which is nothing but 2R. That means when when length increases, resistance increases. So R is directly proportional to L. Okay. So by combining these two equations, we can write resistance is directly proportional to L by A.
Yes.
Okay. So resistance is directly proportional to L by A. Then here we can introduce the term which is called resistivity. So R, the resistance, this is L by A, directly proportional to L by A. So R is equal to L by A, which can otherwise be called as resistivity into L by A. So R is equal to rho L by A, and this rho is called the resistivity of the material. Okay. Again we know V is equal to I into R. So in place of R we can put as I into rho into L okay. So you can put V is equal to I into R, which is equal to rho L by A. Okay. So No, I have come up to like R is equal to R is L by A. Okay. So R, if we put a constant which is
Proportional
resistivity is equal to R is equal to rho L by A. Rho is equal to resistivity. Now you know V is equal to IR. So replacing R by rho L by A, you get a term V is equal to I into rho into L by A. Okay. So here actually current per unit area, I by A is called current density. Okay. So here we can introduce a term called current density. Okay. So I by A you can call that
J.
current density.
Represented by J.
Density J. And this is the current density J. Okay. This. So SI unit of current density is ampere per meter square. So ampere per meter square is the SI unit. Okay. So that is current density. Further, if E is the magnitude of uniform electricity in the conductor whose length is L, then potential difference across the ends is E into L. So there is something called electric field. Okay.
Yes.
So electric field is related to it is voltage into length, that you know, like there are two surface gap between them is L.
Equipotential
Equipotential. So electric field, voltage is equal to electric field into L. So voltage, these two surfaces are at like you have one surface, you have another surface. So difference between those two surfaces V. V, and if the length is between them is L, then V is equal to E into L, right?
Yes. E is equal to dV by dx.
So voltage is equal to electric field into distance, right?
Yes.
That you have studied in the previous chapter.
Yes.
Voltage is equal to electric field into distance. Okay. So voltage is equal to electric field into distance. So then that's how we have come up to the equation, like okay, V, now V we can write as, so this V we can write as E into L. Okay. E into L, right, is equal to I into rho into L by A.
Yes.
Right?
Yes.
So I into rho into L by A. This is what we have proven. So now L cancels. Okay. And L and L cancels. So E becomes current density into resistivity. That is the electric field.
Which is current density by conductivity.
So E is equal to current density into resistivity. J into rho. Okay. So E is equal to this, you can say J into rho, right? J into rho. So J is equal to E divided by rho. Okay. So J is equal to E divided by rho.
1 by rho is conductivity.
So 1 by rho is conductivity. So this conductivity
J is equal to E into sigma.
So sigma into E. Okay. Sigma into E. Okay. So this sigma is called conductivity. So we have introduced so many terms here. Okay. Sigma, so J we have called it is current density. Right?
Yes.
Sigma we called as Sigma we called conductivity, which is reverse of resistivity. So R is resistivity. So we have defined what is current density, what is conductivity, and then we told what is electric field. Electric field is nothing, potential is nothing but, potential is nothing but E into L. So knowing all these things, you come to this conclusion. Just have you can remember this. This is very important equation. See, there can be a numerical. Okay, the length of the conductor is doubled, the cross-sectional area is halved. How the resistance will change? Okay, there can be n number of numericals based on this. Okay, or you need somebody will ask what if knowing the current, if this is the area of the conductor, what is the current density? Okay, so current density we have found out the current density.
Current by area.
That is current by area. So I by A. So one term we have forgotten here. Current density is I by A. Okay. That term also we have to do. Okay. So E, your electric field is equal to current density into your resistivity. So again, your current density is equal to E by resistivity, which is nothing but conductivity into electric field. Okay, and take a picture. So conductivity is reverse of resistivity. Resistivity is a constant. It's a material property. For different material, there will be different values of resistivity. A good conductor will have higher resistivity. A bad conductor will have higher resistivity. A good conductor will have lesser resistivity. So the resistance not only depend on resistivity, it also depend on the length of the conductor and area of the conductor. So higher is the area, lesser is the resistance. Higher is the length, higher is the resistance. So resistance depend on length, cross-sectional area and resistivity. Okay, so length and area are the geometry. See, in materials resistance depend on geometry and the material type. Okay, so let us say copper is a good conductor. That means its resistivity will be less.
Yes.
Conductor copper will have less resistivity. Whereas a insulating material.
It's a good
Not insulating.
Insulator.
A poor conductor, insulator. It will have higher resistivity. Okay. So with this we can solve good number of numerical. Okay. So then we have studied earlier like the Ohm's law B equal to I by R and all that. Okay. So now going to the details of resistivity and temperature difference. So you just have a look what I have written here. Okay. So one is your current density. Okay. One is your current density. Okay. Another one thing we are told resistance is inversely proportional to area. Okay. Then another thing we told that resistance is directly proportional to length. Finally, we come to equation R is equal to rho L by A. Then we told potential difference is equal to electric field into length. Then knowing this electric field into length, then E is equal to EL we know. Okay. So we have equated two equations. Okay. We have equated two things. One is voltage is equal to EL, another is equal to voltage is equal to I into R. By simplifying this, you come to another equation. E is equal to IA into rho. So E is equal to IA. IA is nothing but your current density. So J into rho. Okay. So J becomes E divided by rho. 1 by rho. 1 by rho is nothing but your conductivity. Sigma is your conductivity. So clear till this point?
Yes.
You can derive.
Yes.
There are two equations we are equating. Okay. Let us say this is equation 1. Let us say this is equation 1, and let us say IR we wrote na, I into rho L A. Okay. Let us say this is equation 2. These two equations you are equating. Equation 1 and 2 you are equating, and from there you are finding like, okay, E is equal to I by A into rho, and then I by A is current density J into rho. J is equal to E by rho. So current density is equal to conductivity into electric field.
Yes.
Clear?
Yes.
Current density is equal to conductivity into electric field. This is also a converter. Okay. Okay, so let us talk about resistivity, which is a property. So let us discuss about resistivity of different materials. Okay, as I was telling that copper will have lesser resistivity, and what is the unit of resistivity? So those things we need to know. Okay,
Yes.
right? So the what is the we need to have a feeling of order of magnitude of resistivity, right? You need to have a feeling of order of magnitude of resistivity. You need to have a feeling of order of magnitude of resistivity. Okay. So we have a table resistivity of various materials. Okay. So good conductor and bad conductor or insulators. Okay. Uh, you can refer to them afterwards, but you just know like, okay, what is the unit of so we have told R is equal to rho L by A. Okay, that's what we have told. Okay, so resistivity R ohm at degree centigrade ohm. Okay, how come it is ohm?
Resistance is ohm. Resistivity is ohm meter.
Ohm meter. Yes, that's the unit. Okay, so because this is ohm, this is rho,
Meter square by
this is
meter.
meter by meter square. Meter square, that implies rho has unit of meter will go other side, so it will become ohm into meter.
Yes.
That is the unit of resistivity. So the a typical value, let us say conductors, okay, like silver, copper. Okay, so silver, what is the value? Silver is 1.6 into 10 to the power minus 8. Just have a look. How much it is? Silver, 1 minus 8.
Yes. Resistivity.
Resistivity. So rho copper 1.6 into 10 to the power minus 8.
Yes.
Okay. So copper 1.7 into 10 to the power minus 8 ohm meter. Ohm meter.
Yes.
Here. So aluminum has still better. Aluminum we use for overhead conductor, that is 2.7 into 10 to the power minus 8 ohm meter. Okay. So you can say almost like aluminum is 1.5 times more better conductor than copper.
Yeah.
So these are some of the conductor, and let us say there are so these are conductors. Then let us go to the semiconductor. Okay, there are semiconductors whose and then insulator. Okay, so insulator will have higher resistivity. So these things will have lesser resistivity. Semiconductor will have higher
Right.
resistivity. Conductors will have still higher. Sorry. Conductors will have lesser resistivity. Okay.
They let
Huh.
electrons.
Then insulators will have higher
Higher
resistivity. So we can take example of a insulator,
Plastic.
like say,
Plastic.
huh, like say glass. Okay. So these are all conductor. Then let us say go to a insulator, that is glass. Okay. So here conductors will have lesser resistivity.
Yeah. Because they let electrons pass.
Mhm. So glass will have this will have lesser, glass will have more. Okay, glass its value is some 10 to the power 13 to into 10 to the power 16 ohm meter. Such a high value. That is 10 to the power minus 18, whereas uh, 10 to the power 10 to the 10 to the power 10 to the power 10 to the power 16. Just have a look, it is 10 to the power 10, 10 to the power 16 or not.
Yes, 10 to the power 10 to 10 to the power
Six.
14.
14, huh?
Yes.
Oh, so this is 14. So you can imagine how many times the resistivity is more for a glass as compared to
A conductor.
a conductor. And in between comes some semiconductor. So germanium, silicon, carbon, these are semiconductor. So one example of semiconductor. No, so the semiconductor, let us say silicon is a semiconductor. So these are all we are studying about material in your periodic table. Okay. The semiconductor is silicon. So silicon has a resistivity of 2300 ohm meter. Clear?
Yeah.
So this is 10 to the power 10, very huge number.
Very high.
Insulators. This is
Moderate.
somewhere in between 2300. So you can say this is like 1000, something like 10 to the power 3 or something. This is 10 to the power 3.
Yeah.
This is in the order of 10 to the power minus 8. This has increased to 10 to the power 3.
Then 10 to the power
Then it is something like 10 to the power 10 into 14.
14.
So this is how the order of magnitude you should remember. Okay. These are order of magnitude of resistivity of different material. Okay.
Yeah.
Then we'll study something called temperature dependent of resistivity. Okay. So your resistivity at any temperature T, we'll put it in a different. Your resistivity at any temperature T is equal to resistivity at 0 or whatever absolute temperature, or we'll see what temperature it is, into 1 plus alpha into T minus T0.
Yeah.
This is the resistivity at any temperature with respect to a reference temperature. Let us say reference temperature is known as original, O or original. Okay. So the temperature, the reference temperature is T0. The resistivity at T0 is rho 0.
Yeah.
Okay. So this is called this equation is very very important. You can have some numericals on this also.
Yeah.
So resistivity at any temperature is equal to resistivity at original temperature into
1 plus I
one.
into
However from it comes actually, because you are writing rho t is equal to rho 0 plus some rho 0 into alpha into t minus t0. That's this additional, in addition to rho 0, this additional term will come.
okay.
This additionally, this is called like coefficient of thermal expansion. Similarly, this is coefficient of resistivity or the thermal coefficient of resistivity. This alpha is called thermal coefficient
Of resistivity.
of resistivity. Clear?
Yes.
So thermal coefficient of resistivity. So the original resistivity has increased by this much magnitude
That is an
because of
extra amount.
extra amount increase. That extra is what? That extra is
Rho into
rho,
temperature
so
difference.
rho 0 into coefficient of thermal expansion and this thing.
The
Because
temperature difference.
in your solid mechanics we have studied that what is expansion. Okay. You like say we had a rod. I think I have taught that we have a rod. Okay.
Yeah.
I have a aluminum or iron rod. Okay. So if I heat it, it will get extended. Okay. So that by how much it will get extended. So let this length be L, let this length be delta L. So it is used to get extended by delta is L is equal to coefficient of thermal expansion into delta T.
Temperature difference.
So this is called coefficient of thermal expansion into the temperature difference. That is the change in
Temperature
change in
before
length
and
is
after.
equal to so alpha into delta T. Then you used to have strain, thermal strain del L by L, then alpha into delta T divided by the original length. Then thermal stress will become sigma into E into the strain. This is strain, thermal strain. E into E, so E alpha delta T by L. Like that we used to do. That is the thermal stress.
Yeah.
Thermal stress is equal to E alpha delta T by L or whatever. Right?
Yeah.
So this is something similar to that. This is called thermal coefficient of resistivity. Okay. So now we will try to do a numerical on thermal resistivity. We will try to do a numerical on resistivity. Okay. You take. So we have studied about conductor, we have studied about insulator, we have studied about semiconductor. We told conductor resistivity in unit of resistivity is ohm meter. Conductor resistivities are in the order of magnitude 10 to the minus 8.
Yeah.
Semiconductor resistivity order of magnitude 10 to the power 3. So 10 to the power minus 8 to 10 to the power 3, then it will go up to 10 to the power 10 to 10 to the power 4. 14 in case of insulator. Okay. So you can imagine like for glass it is a complete insulator, it will not at all carry electricity. So this all this resistivity depends on the free electrons present. Okay.
Yeah.
So if you have more free electrons present in the structure, it will be better conductive. If you have less free electrons, it will. So with all this conductivity, it all depends on the free electrons. It all depends on electrons. So when you apply a potential difference, so the electron will start moving in a particular direction. The negative charges will start moving towards the positive direction.
Yeah.
So if you have more free electrons in the substance, if you have more free electrons, you will have, it will be better conductor.
Conductor.
So when you, there will be lot of free electron in the material. So when you put a battery, you have a positive charge, you have a negative charge. So the electrons will flow in a particular direction. That is called direction of current flow.
Yeah.
So electrons will flow from towards the positive. Okay.
Negative to
Electrons flow from negative to positive, whereas current flow from positive to negative. That is the normal convention. Okay. So that. So now we'll try to solve a numerical. So these are in your 12th, right?
Yeah.
This chapter is, this current Ohm's law is after electrostatics.
Yeah.
Okay. So I assume that you have understood Coulomb's law, electrostatic properly, and you can solve numericals on that.
Yes.
Because there will be n number of numericals on Coulomb's law. That Q1, Q2 by R square.
Yes.
Okay, the force, electrostatic force.
1 by 4.
Okay, so we have this current is flow of current. This current is flow. It is a flow, but it is like in statics, you have statics and dynamics. Here you have electrostatics and electrodynamics. What we are studying is electrodynamics because the electron has started flowing.
Flowing due to current.
Yes. Okay. So we'll do a numerical. The resistance of a platinum wire of a platinum thermometer. Okay, so you have a thermometer.
Made of
Okay,
platinum.
at ice point is 5 ohm. Okay, what is ice point? 0 degree centigrade or 273 degree Kelvin, right?
Yes.
At ice point, the resistance of thermometer. Okay, so the at ice point, its resistance is 5 ohm.
Okay.
Okay, that's the thing. And at steam point, what is steam point? 100 degrees centigrade. How much is it? 373 Kelvin.
Yes.
How much is the resistance becoming at steam point? How much is the resistance becoming at steam point? 5.39 ohm. 39. Okay. So this is condition A, this is condition B.
The increase in temperature.
Increase in temperature. Okay. When the thermometer is inserted in a hot bath, the resistance is 5 volts. So now you are inserting the thermometer in a hot bath. Inside a hot bath, resistance of the platinum wire. So in a condition C, let us say some hot bath or something is in hot bath. Okay, some little higher temperature. Okay, he has not told what is the temperature. Hot bath, the resistance of the platinum wire is, it has become 5.739 ohm. 5.795, sorry. 795 ohm. So this is 3 conditions.
Okay.
Calculate the temperature of the bath. Okay. So we know everything. This is my question. What is the temperature?
Okay.
Okay. So to know this, so to know this, first you have to find what is the resistivity. Okay. So you develop the relations between A and B. Okay. Okay. So RB is equal to R R0 RA into 1 plus alpha into delta T, right?
Yes.
So RA is equal to 5 ohm into 1 plus alpha into 100, right?
Temperature.
Huh. So RB is equal to 5.39, correct?
Yes.
So how much is my alpha?
0.39.
So it will become 5.39 minus 5. Okay, so 5 divided by 100. How? Because 5.39, then you expand it, is equal to 5 plus alpha into 5 into 100, right?
Yeah.
Alpha into 5 into 100, so it will be 500, right? 5 into 100, right?
Yes.
Alpha into 5 into 100, okay? So your alpha will become 0.39 into divided by 500, okay? So 0.39 if you divide by 5, it will come something around 0.08, right? 0.08. Then before that we will put two zeros.
Yes.
So your alpha become 0.008. Okay. So now you want knowing the alpha, you can find out what is the
Temperature of heat bath.
temperature of heat bath. So now you come to A and C, right? Now you come to A and C. So you know my initial in 5.795, okay, my 5.795 is equal to initial temperature, initial is taken 5 into 1 plus 1 plus, then I know my alpha, I got it, 1 plus alpha t na, 0.0008, okay. Then I have this delta t.
Yeah.
Correct. So my delta t will become 5.795. Okay. It will become 5.795. 5.795 minus 5. Okay.
By 5 into 0.0.
5 into 0.008. So that will be 8 by 40. Okay, so it will become 0.004, right?
Yeah.
0.004. Okay, that's all. No?
Yeah.
So it become, let us say 0.8. Okay, let us say 0.79 is something like 0.8.
Okay.
And this become 0.004, right? So this becomes like 8 into 10 to the power minus 1 divided by 4 into 10 to the power minus 3, right? So this becomes 2 into 10 to the power 2, right? This will become 10 to the power minus 3 goes to the top, it will become 10 to the power 2. So it becomes 200. T is 200, okay?
200
If T is 200, that means this is 0, this is 100, okay? So C will become, hot bath temperature will be 200. 0 plus 200.
Yeah.
So the answer is, okay, the answer is calculate temperature of the bath. Two hundred.
In Kelvin they told. Have they told in Kelvin?
No, Kelvin does not matter now. Kelvin does not matter here because you are writing in the delta T, right? It's a difference. Or, okay. So, T. 345, okay. 0 plus in between A and C. Alpha, is there any mistake in the alpha? Did you make any mistake in alpha?
Calculation.
This is 100 now.
Yeah.
Okay. 100. What mistake we have done in alpha? R rho oh, okay, some resistivity is also there. Okay, that is alpha only.
Alpha is the thermal coefficient.
Yes, sir. Okay. So 5.39 minus 5.39 by 500. Okay. Delta T is 100. Okay, 500.39 by 500. 0.08 divided by 0.08. Okay. So alpha we know 0.008. So now my resistivity has become 5.795 into 1 plus alpha into delta T. Okay. Minus delta T. Okay. Why instead of 0.008, why we have put 0.004? Any idea?
Put 008 only.
Why did we put okay 008 we know na? Why have we put 004 there?
5 into.
No. This delta T 5.795 minus 5.
5 into 0.008. We multiplied that.
5. Okay.
5 into 1, 5, then 5 into 0.008.
Okay. That one.
40 will get.
004. So 0.8 divided by 004. So 8 into 10 power minus 1. 4 into 10 power minus 3. So which is 200. Okay, I think this should be 200 only. That what I feel. Right, then T should be 200. Right. If this is 0, this is 100. That should be
How
200.
much is given?
Here in this book, they have calculated. Okay. So what they have done here, is they have followed a different approach in your book. So we are getting 200, right?
Yeah.
So in your book, what they have done is their approach is something like this. So they are saying R0, R100, RT. Okay. They are saying R0 is 5 ohm, 5 ohm. Okay. Then R100 is equal to 5.39 ohm, and then RT at some other temperature is 5.795. 795. Okay, these three things they are doing, and then uh, uh, let us see, we'll write the equation. So R100 is equal to R0 into 1 plus alpha,
into
1 plus alpha into 100.
delta.
Delta T is nothing, 100, right?
Okay.
R100, okay. RT is equal to R0 into 1 plus alpha into some temperature T, let us say that is 100, then let us say this is delta T. Because it is 0, you can just write it as T, right? Okay.
What
T.
is 0? The temperature difference.
Initial temperature is 0, na?
Okay.
R0
Second
is at
equation
0.
is for
Yeah.
first condition.
Second equation is for temperature T, which is unknown. We have to find out. Okay. So we know alpha in both the cases will be same. So what will happen? Let us say equation 1 and equation 2. Alpha will be same, we will develop a relationship. Okay. So R100 minus R0, R100 minus R0 by 100 is equal to alpha.
Yes.
Right?
Yes.
R100 minus R0 by 100 is equal to alpha. Similarly, RT minus R0 divided by T is equal to alpha.
Alpha. Equal.
So this is equation number 3, this is equation number 4.
4.
Because alpha is a property, it cannot change. Okay. So now we can write R100 is equal to 5.39. 5.39 minus R0 is equal to 5.
By
Okay.
100.
By 100 is equal to RT. RT we have told RT is equal to 5.739, 5.795. 5.795. Okay, so 5.795, 5.795, then R0 is equal to 5 divided by T. Okay.
T we have to find.
Yeah, like your book, it's a NCRT book, but they are giving wrong things actually. Instead of 5.39, they have put 5.23. That's the problem. Okay. So if you solve it, you can find it out. Okay. So it will become 0.39 divided by 100 is equal to 0.795 divided by T. So T is equal to 795 divided by 0.4.
Yes. Into 100 that you multiply.
0.4. This is 0.795, sorry. 0.795 by zero point 0.4. Okay. 0.795 by zero point 0.4. So it becomes something like 800 by 4, which is
That
around 200.
0.795 into 100, no?
No, 100. This is 0.39, this is 100. Okay, 0.795
into 100 by 0.4.
Alright. Okay. So 0.795 into 100 by 0.4. You are correct, sir. Okay. You are correct. Okay. So this becomes 79.5
by 0.4.
by 0.4. So this becomes 795 by 4, which is again around 200 degrees. So what we have derived earlier is correct only. In your book, there is a printing mistake. Instead of 0.39, they are using 0.23.
Oh, wait.
You can see instead of 0.39, they are using 0.23. This is a NCRT book, but there is a mistake here.
That will make
That
a
is-
huge difference when you divide.
If you make it 0.23, it will be
Point 4 and point
हाँ,
2
it
is
will,
so much
so it will
difference.
be in the 4 it will become 2 and it will become 400.
Around
So what we
300
have
something.
calculated earlier is correct only 200. So either way you calculate it is 200 only. Okay. So that there can be numerical on this. Okay.
Yes, yes.
You take
There
a
are
picture.
two numericals like this.
Yeah, you can find out from your CT paper how many numericals are related to this. There can be, see, one
There is always
numerical,
one initial
one
condition.
numerical is R is equal to rho L by A.
Hmm.
Another is temperature dependent of this resistance. Okay. And the order of magnitude of different conductors. Okay. So this NCRT book example itself, there is a typo. Instead of 0.39 they are using 0.23. Okay. So next we will discuss after this conductivity, mobility and all that. Okay. So today you have understood what is electric field, what is potential and
Relation between electric field and potential.
that relationship what I have shown earlier. Okay.
E is equal to.
So what I am teaching you have to refer the video.
Yeah.
You have to refer the board. Whatever I am teaching, unless you refer it and see it for half an hour or 45 minutes, you will forget everything. What teacher teaches, you have to listen, you have to look into it for at least 30 to 45 minutes. That's why I am recording the video.
Yes.
Okay, thank you.